Now, hello and welcome. In this video, we are going to look at the marking scheme of paper 1, multiple choice of higher physics. And let's go straight to the first question. We are just going to look at just some of the questions which I consider to be, there is a lot to learn when we look at such questions. So let's go straight to this first question. In this first question, you are given that a ball is thrown vertically upwards and falls back to its starting position. The acceleration time graph represents the motion of the ball. Which of the following velocity time graphs represents the same motion? So the motion of an object can be represented using three types of graphs: a displacement time graph, a velocity time graph, and an acceleration time graph. So one type of graph can be extracted from the other. In doing that, in this particular question, I'd like you to observe that the acceleration is negative here, because it is in this quadrant here. It's negative and it is uniform over the whole period of flight of the ball. So the object has been thrown upwards and then it comes back to the starting point. How much is the displacement? The displacement is 0, because the distance from its starting point to where it is after that duration of flight is actually that length of the path is 0, and therefore the displacement is 0, although the distance has a value. Distance can never be 0. So let's start with the first part. The acceleration is uniform and it is negative. When it comes to velocity time graphs, we must remember that the acceleration is given by the gradient of the graph. Number one, the gradient of the graph, of the velocity time graph, must be constant throughout the whole motion. When it is moving upwards and downwards, it has got the same acceleration. And then next, it must be negative. It must be uniform and negative. And when you look at the choices, you can see that the best choice here is A. It is A. So that is why I thought this part of the question was very interesting. Over here, we are taking the velocity upwards to be positive. I mean motion upwards to be positive. That is why this part of the graph is in the positive quadrant. So it means that when the object is coming down, is moving downwards, of course, the velocity is going to be negative. At this point, it is at its maximum height. This area here represents the height covered, while the other area represents the height that the ball falls. And the two are equal, because if it rises 30 meters, it must come back to the starting position again 30 meters. That is why this area and this area, they are the same. But one area is positive, the other one is negative, meaning that when we put them together, you get a displacement of 0. Remember, the area and a velocity time graph represents displacement. So that is why this area and this area, they must be, one is positive, the other one is negative. Secondly, they must be of the same magnitude, so that when you put them together, you add them together, you get 0 displacement. This other graph here, it would not be correct, because when I calculate the gradient of this line here, I find that although it gives me acceleration, that acceleration is positive. It's positive, but the acceleration for this object is negative. You know, when you throw an object vertically upwards, the acceleration you take for the complete motion, even when it reaches maximum height and start moving down, must be the same, and it must be negative acceleration due to gravity. So that is why we ruled out D. We also rule out E, because in E, this will be a speed time graph. a speed time graph. In speed time graph, even when the velocity is negative, we treat it as positive, so that when we add this area and this area, we are going to get the total distance covered. For example, 30 meters plus 30 meters, 60 meters. That would be the total distance covered. But when it comes to the displacement, it will be 30 plus minus 30, we get 0. And that is why, again, A is the best choice, or the correct answer, so to speak. Let's look at question number 2. In question number 2, we are given that a student uses the apparatus shown to determine the acceleration of a trolley as it moves down a ramp. This is just like a plank of wood that is flat enough, long enough, like for example 5 meters, and then it is inclined at a certain angle. And then we've got a light gate here. Light gate works in such a way that when this trolley moves down the incline, you'll find that this card is going to cut off the light. When the first section of the card touches that dotted line there, a stopwatch is automatically put on, or it starts counting. And then when the end part of it is reached, it stops. So it's going to measure a certain time interval. Let's read and see what kind of time interval it is measuring. The trolley is released from rest, so U is 0 at this particular point, and moves down the ramp. A card attached to the trolley passes through a light gate at point Q. The time for the card to pass through the light gate. Observe here, the time for the card to pass through the light gate is displayed on the electronic timer. In other words, the time that is displayed on the electronic timer is the time taken for the trolley to move through a distance equal to the length of the card. So although the velocity here is 0, it starts from rest, but by the time it touches this card, it just touches this dotted line. That is where we get our U. When it just leaves that line after traveling a distance equal to the length of the card, that is the time we get V. So when they tell us that the vehicle's acceleration is determined using the relationship v squared is equals to u squared plus 2as, and the student makes the following statements. The student makes the following statements about the terms u, s, and v, and says that u is 0. U is 0, and then s is the length of the card. This is correct. S is the length of the card. U is definitely not 0, because by the time this card touches this line here, it's got a velocity, a high velocity in fact, because it's moving down the incline. So the velocity is already high. So U is not 0. So here, when we are told that the trolley is released from rest, it's true if the S was the length of the whole of this path from this point all the way to this point. But now the acceleration, the time that we are interested in, is a time taken to cover the distance equal to the length of the card. Like for instance, in part 2, we are saying that S is the length of the card, which is true, because the time that we have measured here is a time taken to travel through a distance equal to the length of the card. Let's look at part 3. V is the distance between P and Q divided by the time displayed on the card. Of course, this is not true, because the time that is displayed on the electronic timer is the time taken by the trolley to travel a distance equal to the length of this card at this point here. So when we look at these options here, which of these statements is or are correct? You find that 1 is not correct. U is not 0. It has a value. 2 only. S, the length of the card. And I tend to agree with this, that it is only a part 2, statement number 2, that is correct. Let's look at C, 1 and 2. Of course, we've ruled out 1. D is out because we ruled out 1 and 1 appears to be included. And E is, of course, out. We ruled out 1. So I tend to think that the best choice would be B, where it is this option that is correct. Let's go over to question number 3. Here we can do a bit of calculation. A spacecraft unloads cargo on the surface of the moon. The gravitational field strength on the moon is 1.6 newtons per kilogram. The package of mass 3 kilograms moves down the ramp. The component of the weight of the package acting parallel to the ramp is how much? This one is very easy because this is how we would work it out. So let me get let's look at the forces now, or that is acting on this package. One of them is the weight of the package. So over here, this is the weight of the object, which we should be 3 kilograms times 1.6 newton per kilogram. I think that one gives us 4.8, sorry, 4.8 newtons. Then the component of this weight down the incline, which is given by this arrow here, will be equal to mg sine 34. So we are going to have 4.8 sine 34 degrees. I think we can be able to work out that one and compare it with the values that we have here. Let's do exactly that. Now this one will give us 4.8 multiply by sine of 34, and we're going to get 2.684 recurring, 2.684 newtons. To two significant figures, this one should be 2.7 newtons, and that is why B is the correct answer. And let's go to the next question here. This is about tension in strings. And let's read the question together. 2 blocks are suspended from a ceiling by ropes as shown. And we are told that which row in the table shows the tension in the rope at point X and the tension in the rope at point Y. For us to be able to work out that one, we need to show the forces which are acting on this block here. This block. I will start with the one at the bottom. And one of them is the weight of this block, which will be 15 times 9.8 newtons per kilogram. That one, of course, gives us 15 times 9.8, and we get 147. So that is the weight of this block. In other words, the earth pulls this block downwards. This string here also pulls it upwards with a certain amount of tension in string Y. Okay. And the same string or rope pulls this 12 kg block with the same amount of force equal to Ty. But when we look at the 15 kg mass, you can just see that there are just 2 forces which are acting on it. The tension in the rope acting vertically upwards and the weight of the block. So this tells us that the tension in the rope Y is 147 newtons. So tension in Y is 147 newtons. So having said that, we'll come to the 12 kg mass. 12 kg mass. Again, there are actually three forces which are acting on the 12 kg mass. So one of the forces which is acting on the 12 kg mass is the tension in Y. In other words, the rope Y tends to pull this object downwards. The other force which is acting on the 12 kg mass is the tension in X, which tends to pull the 12 kg mass upwards. So let me just put that tension in X. I'm going to draw an arrow like that, and then I say tension in X, pulling the 12 kg mass upwards. And of course, the third force is its own weight, which is 12 again times 9.8, and that should give us 12 times 9.8 gives us 117.6 newtons. Again, when you look at the 12 kg mass, it is in equilibrium, so the resultant force on it is 0. That means the sum of upward forces which is acting on it, which is Tx, is equals to the sum of the downward forces, which is equals to its own weight, 117.6, plus the tension in Y, which is 147, I think 0.0 there. Let's see what we get. So 117.6, we add 147, and we get 264.6. 264.6 newtons. Now when we look at the choices, of course, we can see the tension in Y. It will be easier to identify that. Tension in Y should be 147. So this appears to be like 115 newtons if we round it up to two significant figures. So it is either C or E. Otherwise, the other one should be 264. Let's see. Yes, this one, 260. Again, two significant figures, that is 260 newtons. So the best choice is E. Let's look at question 15. Question number 5. During an experiment, a student inside a lift stands on a Newton balance, and the mass of the student is 50 kilograms. The lift accelerates upwards at 1.2 meters per second, and the reading on the Newton balance is, we have to calculate the reading on the Newton balance. Now, for us to do that, we must realize that the type of force that the balance reads is called the normal reaction. So we'll come here and show the forces which are acting on this man here. One of these forces is the weight of this man, his weight, which is 50 times 9.8, everything newtons. The other one will be the reaction from the balance, like that. The surface of the balance tends to push him upwards. Now this balance, for it to read the weight of that particular person, it gives us the reaction. So if we are able to calculate the reaction, we'll be able to get the reading of that balance. But we are given some information that this system is accelerating upwards. It's accelerating upwards at this point. So if it is accelerating upwards, what that means is we've got to resolve these forces upwards and equate it to MA. So this is what we're going to do. We're going to say that the resultant force on that person is equal to MA. The resultant force, since the acceleration is upwards, the resultant force must be upwards. That means in order to get that resultant force, I'm going to subtract the weight, which by the way is 50 times 9.8. That gives us 490. F minus 490 is going to be equal to 50 times A, which is 1.2. There are just 2 points that I'd like you to observe here. Let me just first of all work out that one so that I can point out that. So here I get 60, and I'm adding 490, and that gives us 550 newtons. And of course, that is why the correct answer is D. D there. So I was saying that there is a point here that I want to emphasize, and the point is this. When you're given an object like this, you must check the state of the system. If it is in equilibrium, you will know that the resultant force on the object is 0, and therefore you're going to say forces in one direction is equals to forces in the opposite direction. But if the state of the system is such that it is accelerating, like for example in this case, then you must use Newton's second law, which states that this is the resultant force acting on this object of mass m, producing an acceleration A in the direction of the force. An acceleration A in the direction of the force. It means that if you know the direction of the force, you should know the direction of the acceleration. Similarly, if you know the direction of the acceleration, you should be able to know the direction of the resultant force. And that is exactly what I did. I started by observing the direction of the acceleration. This one is upwards, and that is why I can conclude that R is larger than W. That is so important, so that I should know whether to do R minus W is equals to MA or W minus R is equals to MA. For example, if this acceleration was downwards, then I will say W minus R is equal to MA. But now the acceleration is upwards, in which case I should know that R is larger than W, and in order to get the resultant force, I just need to subtract the smaller force from the bigger one. So the acceleration can give us a guide as to how we deal with those two forces. Should it be R minus W or W minus R? You just need to look at the acceleration, the direction of the acceleration. If you know the direction, then you know the force which acts in the direction of that acceleration must be larger than the force which opposes that motion. And that is how you would work out that question. Let me stop at this point. If you like this video, go right ahead and subscribe to this channel, where I will be covering more of such questions. And definitely, if you're a student out there, you're going to benefit from these discussions. Bye bye.